So can I just quickly check now that I switched headphones? Do you still hear me? Thank you.
Okay, so let's start. So hello everyone. Thank you for joining this lunchtime seminar organized by Young Second. Today's talk is about offshore geotechnics, and we have three speakers that will provide an overview on the latest advances in seismic modeling, design, and installation of foundations. Before moving on to the talk, I just want to go through a few things. First of all, let me introduce myself. I'm Marco Beguera. I'm the current chair of the second Young Members Committee, and I'm also the chair of today's meeting. Um, there are also very few housekeeping rules to go over, so please can all guests keep their videos off and microphones on mute during the seminar. We're going to have a Q&A session after all presentations, but please feel free to type your questions in the chat at any point. And please note that the seminars is now being recorded, so will be also uploaded onto the SECED YouTube channel. So by dialing into the event, you consent that any views or opinions you share are being made public. And now, moving on to the talk, I'm very pleased to have today Dr. Stavroula Kontoe, who will provide a short introduction to the topic of offshore geotechnics. And these will be followed by the presentations of two brilliant young researchers, Julia Caterina Möller and Evangelius Kementzetzidis. So, our first speaker is Dr. Stavroula Kontoe, who is an associate professor at the University of Patras and visiting reader at the Imperial College London. Her publication record includes more than 100 papers in topics related to geotechnical earthquake engineering, computational geomechanics, and offshore geotechnics. Her work has attracted multiple awards. She has also been active as specialist consultant and as member of several international and national committees. And very recently, she served as chair of SECED for the period 2020-2022. So without further delay, I will hand over to Stavroula for her introductory presentation. So I'm going to stop sharing my screen and Stavroula, please.
Thank you very much, Marco. As all second, very pleased to introduce the topic and effectively give the forum to brilliant younger researchers. It's going to be a very general introduction, focusing, of course, on foundations. So we have to put a disclaimer here that we will be dealing today from we're mainly focusing on the foundation aspects of offshore wind. But first one, I would like to convince you that it's worth spending an hour and a half on this, and actually a lot more than just an hour and a half that we're going to spend today. The data, the statistics speak for themselves, and it's really astonishing the step change that we saw in 2021. And this is massive. So what is plotted here is new offshore installations in megawatts since kind of the beginning, since 2006 until 2021. And what we see is a massive step change in 2001. The whole trend is upwards, is increasing. And this is partly, but not exclusively, to the growth that we have seen in offshore wind in China. Also, other parts of the world have started participating. And if we see that in a bit more detail, so if we drill into the data of 2021, this time in gigawatts, so change units, we see what these other countries are. And apart from the classic players, so United Kingdom has been a big player for a few years now, or other classics like Denmark, we see also Taiwan and Vietnam starting strong to participate, to plan or develop, in this case, have actual installations of offshore wind. And if we put all the data together, so the total to installations till 2021, to see the countries that participate, we see also more traditional stakeholders like Germany having a big share of the pie. But I think what is also interesting is to see the future. And the future tells us that we need to keep growing. And actually, these predictions do not fully, so these are the predictions till 2031, so the global offshore market outlook till then. And according to the International Energy Agency, this is not enough. So if we wanted to meet net zero globally, then the world needs to install 80 gigawatt annually by 2030 and 70 annually by 2050. So even that we see significant growth, this is not even good enough for net zero. However, what we also see is a number. So if we just try to bring it also closer to the interests of SECID, we see a lot of countries now participating in offshore wind, which are seismic, and not just seismic, places like Japan and Taiwan, which are of a very high seismicity. So there is an interest there. There is clearly an overlap, and that's not the only overlap, the seismic. I will try to flag other issues as well that relate to the interests of SECID. Just because I appreciate that today not everyone is not, it's not a talk in an offshore wind audience, it's in a more general audience. The SECID audience is not necessarily offshore wind audience. So just a very classic figure just to explain that in shallow waters, we tend to have gravity-based structures and the monopiles where they are predominantly subjected to moment and lateral loading. And as we go to deeper waters, we see jackets and tripods, and their axial loading is a key element for the foundations. Now, more recently, so this is more pilot projects that start to more and more appear. We started moving to even deeper water, so deeper than 70 meters, let's say, to floating solutions. But if we see the share of the pie, this is not necessarily from last year, it's for a couple of years back. Monopile is by far the most popular solution, with jackets following through. And while for jacket foundations, we can share solutions and the know-how from the oil industry, because there the loading is not too dissimilar, but the pile supporting jackets foundations have. For monopiles is a new ball game, yeah. And just to appreciate the size, this is a photograph from such a monopile from the wind farm Yulin in Taiwan. And what basically the industry is doing to meet these demands is going to larger and larger sizes. I don't know until when, but that's what is happening the last few years, the trend. And this poses some new challenges. So I am in the fortunate position to set the questions today. Hopefully some of them, not all of them, will be answered by Vangelis and Kika. That's my perspective. Some of the open questions for monopile foundations. I mean, how we drive them. Drivability methods have been developed mostly for not mostly, I would say exclusively for smaller diameter piles. So while they are fit for purpose for foundation piles for jackets, for monopiles, they need rethinking. Yeah, because these are essentially empirical methods, which they give us the resistance to driving. So, but we can estimate what type of hammer, what the size of hammer we need to drive safely this type of foundations in place. And I think an evidence of that is the recent incidents we've seen. For example, this is from again from Yanlin, where they saw I think one last year and one this year cases of monopile slip. So basically they lost the monopile under self-weight without even having to drive it. So this is an indication, I think, a very good indication that we need to understand and develop better methods for drivability for this, I would say, new type of structures. We have not been dealing with them before. And as monopiles get bigger, because drivability itself, because it's impact driving, is wave propagation, so it's very relevant to the remit of SECED. And as monopiles get bigger, noise from these vibrations gets more challenging to control, and the methods that we develop, and there is a lot of innovation in this field, it becomes more challenging in order to protect the environment and the marine mammals that live in the vicinity. On the design aspects, there is a robust methodology now on the lateral loading, but this is under monotonic loading. So I think possibly Vangelis will touch upon that. There is a lot to be done for cyclic loading, and it's not an easy issue. Yeah, we cannot explicitly model every single cycle of a storm loading or wave loading. So we come up with approximate solutions, and to my mind, these are promising, but they are still in work in progress. They have not matured to the level that we have for monotonic loading, particularly because we have very strict performance criteria, and we need to be able to predict the movements, the deformations accurately. And a last question, maybe not as pressing as the previous ones, is what about the long-term performance? Can they last beyond the design life? Can we rely on the foundations to keep them for longer than 20, 30 years? That is the current design life to support bigger and bigger towers in the future. And moving on, and that's my final slide, to the challenges for the seismic response, since we are moving into more and more seismic countries, is the lack of case studies. We have life expectancy, if you like, but is very short for these structures from the perspective of earthquake engineering. They are very recent, so we have no case studies to support our understanding of how these structures behave under seismic loading. They are considered relatively resistant to seismic excitation because their natural frequencies do not coincide, at least in the horizontal direction, with the seismic range. Kika will show that when liquefaction is in plane, and I don't want to spoil the preview, this can change. So it's not correct to think that they are seismic resistant. Under some conditions, it's not. And they are exposed to a combination of natural hazards. So it's not just the seismic, it's typhoons, tsunamis. We need to come up with procedures without that are economically feasible, but at the same time make these energy systems resilient. And we have to remind ourselves what are the performance limits. So under normal design, performance limits are very strict, less than 0.5 to 0.475 permanent tilt. Can we really design them for such strict performance limits under seismic loading? And if that's the case, for what level of seismic loading we want to achieve that? So we need to set ourselves some code provisions, which at the moment, as far as I know, we don't have. So it was my pleasure sending the questions over to Vangelis and Kika. I'm not sure in which order to deal with some of, hopefully to touch some of on these topics.
Yeah, thank you very much, Stavroula, for your comprehensive introduction. And just want to remind all participants that the Q&A session will take place at the end of the final presentation, but feel free to post your questions now on the chat or at any time. So our next presenter is Julia Katerina Kika Möller, who is a postdoctoral researcher in the geotechnics section at the Imperial College London. Currently working on the development of constitutive models for sands under cyclic loading. She holds an MSc in civil engineering from ETH Zurich and a PhD from Imperial College London. During her PhD research, she investigated the response of monopile foundations for offshore wind turbines under seismic loading. So her technical interests lie in the fields of dynamic finite element analysis and soil liquefaction phenomena. And Kika is also a member of the SECED Young Members Committee. So please, Julia, Kika, the floor is now yours.
Thank you very much, Marco, for the introduction. Quickly check whether you are able to see my screen.
Yes, all good.
Okay, perfect. Then, yeah, many thanks for the introduction, and thanks for the invitation as well to Young SECED. And thanks to everybody that's joined this call to join this presentation on the seismic response of monopile foundations for offshore wind turbines, a research topic that I have explored during my PhD studies at Imperial College. Tying this to set the scene basically and show the motivation behind this research project, and following on from Stavroula's introduction, I'm showing on this slide the current capacity of global offshore wind, as you can see in black here, but I also highlight in white the expected growth in various areas of the world for offshore wind, and especially in the Asia Pacific region, where seismicity can be very high. There's a very large growth predicted, and many new wind farm projects will be built there. But the difficulty, as Stavroula said earlier, is that our current design standards are built on the experience that was gained from wind farm projects in Europe. So seismic hazards such as ground shaking and also liquefaction of the seabed, there's a lack of guidance basically regarding these hazards. And this talk will focus on monopile foundations. So as Stavroula showed, very large diameter tubular steel pipes, which are by far today the most common type of foundations for offshore wind turbines. To design these monopiles, there are three main design methodologies shown here in increasing complexity from left to right. There's a simplified method, the standard design method, and the advanced numerical method. In the simplified method, the entire soil and foundation is replaced by a set of dampers and springs at the mudline level. And these represent the foundation stiffness of the system. So the natural frequency of the entire system can be estimated. Therefore, the accelerations of the superstructure can be derived, and one gets an estimate of the maximum bending moments and loads that would act on the pile head. However, if one is interested in distributions of like internal forces along the depth of the pile, one needs to move on to the more elaborate standard design method, in which the soil is represented by a distribution of springs along its length. And the main focus of this talk is actually on the advanced numerical methods, which provide the most accurate representation of the true soil structure interaction effects, and, for example, take into account also the soil response in the near field of the pile. But since today the most commonly used approach is the standard design methods, it's worth highlighting a few of the limitations of this more simpler approach. Illustrated here is an example for a pseudostatic analysis using the standard design approach, where, as I said, we have distributed springs along the pile, which represent the soil, and these have assigned nonlinear load distribution functions, which are referred to usually as PY curves. And under seismic loading conditions, there are two types of loads that are acting on such a pile. The first are these kinematic loads, which are resulting from shear waves propagating through the soil deposit. And these can be applied in a numerical analysis, as indicated here, through displacement-controlled boundary conditions. Secondly, there are also the inertial loads acting, which are resulting from the acceleration of a superstructure mass. So one of the first difficulties for the seismic design is, if we are looking at the true variation of these loads throughout the shaking history, how do we combine them? If we try to then simplify it in a pseudostatic approach, how are these acting simultaneously on the pile? And if we're looking at the soil deposit that consists of a sand layer, which is expected to liquefy during the seismic event, there's also a lot of uncertainty concerning the choice of the PY models, because there's a multitude of PY curves available in the literature, which account for a reduction in strength and in the stiffness of a soil as it liquefies, but there's still no agreement on which is the appropriate one to pick to account for this phenomenon. Then as well, the expressions that we do have, they are normally based on predictions of liquefaction occurring in the free field, so very far away from the pile, and they would not normally be accounting for any local developments of pore pressure nearer to the pile shaft and results of these soil structure interaction effects. And very importantly, as Stavroula already indicated, the expressions that we have available for such scenarios, they were all empirically derived for quite long and slender piles, and so it's very questionable to extrapolate these existing expressions for very large and stocky offshore monopiles. So because of these many limitations, I investigated the problem in detail using advanced numerical methods, but for the use of these methods, and due to their complexity, there are certain steps of validation that should be performed. The first one was an evaluation of the performance of existing constitutive models for sand to properly simulate the liquefaction resistance of the soil. Then a second check was the response of very deep offshore deposits under seismic loading and in the presence of liquefaction, which unfortunately I have no time today to go into, but I've put the reference here for anyone who's interested. And to further verify the numerical methods, one requires data from boundary value problem tests, which were carried out under controlled conditions. So very useful for such validation are centrifuge studies. And the case study considered here to verify the methodology was done by Wilson at UC Davis. And it considered a cylinder pile with a length over diameter ratio of 25 in a liquefiable sand deposit, a shallow deposit of just 20 meters. But an irregular earthquake excitation was applied at the base, which then resulted in kinematic forces due to the deformation of the profile, as well as inertial loads due to the acceleration of a lumped superstructure mass on top. So this loading scenario and the similarity of the single degree of freedom system to the offshore wind turbine is expected to be close enough to our seismic loading cases in the field that it's a suitable validation studies, and we will just, once we've verified the numerical results, be able to extrapolate it for these much larger dimensions and these much lower slenderness ratios for our stocky offshore piles. Let me give you a very brief introduction on the two constitutive models that were investigated in these analyses. They were both part of the bounding surface plasticity family. The first one, that is referred to as Model 1 in this presentation by Zappali et al., is based on various previous modifications of the original bounding surface plasticity model by Manzari and Dafalias. And it was developed to improve the simulation of cyclic resistance under various stress levels. This is typically presented in CSR curves, so like cyclic resistance curves, where you can see the cyclic stress ratio, so the normalized shear stress amplitude on the y-axis, and the number of cycles that the sample is subjected to until it liquefies, n on the x-axis. And two key requirements for a constitutive model for a liquefiable sand is that it's able to capture what we call the K-sigma effect, so a trend of a decreasing resistance to liquefaction. Can you hear me?
Yes, now, yes.
Okay, so yeah, like a decreasing resistance against liquefaction as confining pressure is increased, and also to match the slope of such CSR curves, so the resistance at various stress levels. And as you can see here, the second feature is one that can be very difficult to capture for certain types of sand, such as the example of Fraser River sand that is shown here, because the experimental data in dotted line shows very, very flat cyclic resistance curves, which many constitutive models struggle to reproduce. So for this reason, I developed a new cyclic formulation, which would enable to capture this resistance, even like for such low inclination of CSR curves. And I have no time to go into detail on the model formulation, unfortunately, but I'm showing here on a phenomenological level the key difference between the two formulations and compared against experimental data. So model 1 by Sapali would, in order to simulate this decrease in mean effective stress until liquefaction is reached by continuously contracting as it is cyclically loaded. And contrary to that, the model 2 that I developed, it incorporates a shear history threshold, which is indicated here in the generalized stress space. And that essentially controls the apparent angle of phase transformation in the model. So while, as I showed earlier, this model is continuously contractive, the model 2 would, after a few initial loading cycles during which the sand contracts a lot, it would increasingly stiffen and respond in the more dilative behavior, basically. And this had a major impact on the CSR curves that I showed in the previous slide, but it will also show an influence on the results in the boundary value problem that you will see in the following. So here you can see the finite element mesh used in the validation study for the slender pile. Since the problem is symmetric, it was possible to only simulate half of it to save computational time. And you can see the two sand layers of a medium dense to dense layer of Nevada sand. And the two soil models I showed, they were calibrated based on element test data here by Möller et al. And here you can now see the simulated predictions of rise in excess pore pressure in blue compared to the experimental data from the centrifuge tests in gray. And considering that this calibration was done using a single set of parameters and even performing relatively well for relative densities outside the range of which it was calibrated, this match was considered to be quite satisfactory. And if we look at the response of this superstructure that is mounted on top of the single pile, again in blue, the predictions against the experiment, the fundamental frequency of the entire system seems to be reproduced well, the magnitudes of the accelerations, as well as here in the bottom, you see the variation of bending moments close to the pile head over time. And if I show an example of like a local extrema, also the distribution of the bending moments across depth was quite satisfactory with the experimental results. So having gained this confidence now in the numerical procedure, we move on to the larger scale, the offshore wind turbine supported by the Monopile Foundations. And we're considering the NREL 5 megawatts reference turbine in this study, which is founded on a monopile with an embedded length of 50 meters and a diameter of 8.5 meters. And to simplify the analysis, the top mass, so like the rotor nacelle assembly, which consists of the rotor, the hub, and the blades, it is concentrated to a lump mass at the top of the turbine tower. And you can see here the simplified geometry that was used in the numerical analysis. As I said, the mass is lumped at the top of the RNA. The mass of the tower and the substructure itself are distributed along the length to be able to simulate also higher modes of the dynamic response. But to simplify the geometry, a constant diameter was adopted across its length, and the wall thicknesses were adjusted accordingly to get the corresponding flexural rigidity as in the reference turbine. And no installation effects were simulated in this study. The offshore stratigraphy, the example that is considered here, consists of 2 layers of sand. So the top 40 meters are again medium dense to dense sand layers of Fraser River sand, for which I showed the calibration earlier, underlined by a stiff clay layer. Here again, the finite element mesh used for this numerical analysis, it's analogous to the validation study presented earlier. So again, due to the symmetry, being able to model just half of the problem, and also the material models that I introduced earlier for the sand layers, as well as a nonlinear hysteretic model to capture the wave propagation in the clay. To understand the dynamic response of this entire system, we take a look now at the power spectrum for the reference turbine. We can see here the frequency ranges for environmental loads acting on this turbine here in the lower frequency range for wind and wave loads, as well as the rotor and the blade passing frequencies from the rotor. And typically the turbine tower itself is designed in a way so that the fundamental frequencies, the first turbine tower frequency, falls outside of all of these external loads to avoid basically resonance of the system. And this frequency here, again, since it's considered a symmetric problem, the side-to-side mode that is indicated here on the right and the out-of-plane fore-aft mode lie very similar for offshore wind turbines. And they are around 0.3 hertz for this reference turbine, which normally for seismic excitations, which have a predominant frequencies like of 1 hertz and higher, these structures are not considered to be very vulnerable to seismic loads if the intensity of the earthquake motion is low to moderate. However, the input motion that was considered in this case study is the 1995 Kobe earthquake, which, as indicated here on the left, actually would exceed most of the design spectra for different seismic areas in the world. And it shows a very large maximum acceleration of half g at about 7 seconds in the acceleration time history. And down here you can see the predominant frequencies of the input motion between 1 hertz and 2 hertz approximately. Applying this input motion now at the bedrock layer below the stiff clay and having it propagate through the deep offshore deposit, we do realize when looking at the development of excess pore pressures throughout the depth of the entire 40-meter sand layers, that basically the entire sand deposit liquefies as the pore pressures rise and reach this dashed line. So the excess pore pressures becoming equal to the initial vertical confining stresses. So both models basically predict a full liquefaction of the sand layer in the offshore deposit. And if we now consider the accelerations across depth through the deposit, we do see that from the base input excitation to this interface between the clay and the dense sand layer, there's a strong amplification of these higher frequencies around 1 to 2 hertz. But interestingly, when we look higher up now into the top of the soft and liquefied sand layers, we see quite a strong shift of the predominant frequencies towards the left, so towards like lower frequencies, which gets very dangerously close to the fundamental period of this turbine tower. And we do see, when we then look at the response of the wind turbine at hub level, that actually I'm showing here like the amplitude, the Fourier amplitude in the for both the fixed-based second mode of the turbine tower as well as the first mode. And we do see very clearly that it's not only the higher second mode that is excited, but also this first frequency of the turbine tower is excited quite strongly, suggesting resonance in the system due to this very soft excitation from the liquefied soil deposit. And this is the first key conclusion of my presentation, that this behavior should not be neglected generally, considering the choice of and the design of this wind turbines, considering the first frequency mode. Considering the differences between the two soil models, it's best illustrated looking at these animations of the two analyses, in which you can see not only the deflected shape of the system throughout time, but also contour plots of the excess pore pressure ratio. In this, a red contour would refer to a fully liquefied soil, and the blue one, no rise in excess pore pressure. And as you see for the original model, as the motion is applied quite abruptly, like as the main shock of the earthquake passes, we see basically the full sand deposit liquefy, and only like very near the pile shaft, there are some minor fluctuations of pore pressures close to the pile. We compare this now and then we see like as the pore pressures start to dissipate towards the end of the analysis from the propagation from bottom up. But if we compare this to the model 2, which considers a increase in the dilative tendencies and in the stiffness of the soil due to the pre-shearing effects, we do see that even though the entire deposit liquefies in the far field, that there's quite a visible area near the pile shaft, like this cone-shaped area here, in which we observe higher mean effective stress levels than further away from the pile. The implications that can have on the loads that are acting on the pile become clear when one considers the displacement mechanism of the structure. So during an earthquake event, as these kinematic loads are acting on the soil and on the foundation, I'm showing here like one of the local extrema of the horizontal displacements of the pile head, and plotting the contours of vertical displacements in color on top. And these do indicate that we observe heave here towards the right on the back of the pile, and settlements at the front of the pile. This may be surprising when one compares it to the active pile loading case that we are more used to from the design of these wind turbines in non-seismic areas, so where the main loads are coming from wind, wave loads, that would basically push the pile over at the top, and that would normally then result in heave at the front and settlement at the back. But for this passive pile loading case, which correspond to what we observed in the numerical analysis, we do see that as the soil is providing these driving forces, it is pushing against the pile. And if you remember now the animation of the previous slide, a increased strength of the soil might, for this reason, not be conservative if suddenly, when the soil is not what is supporting providing the supporting forces, but the driving forces onto the structure. And this is also apparent here when we compare the bending moments derived from the two different analyses. So in this case, the model 2, which exhibited these higher mean effective stresses locally near the pile, also showed higher bending moments. And since none of these local pore pressure developments would be considered in standard design procedures, there is a disclaimer to be made that these might not in any case be conservative. And the last point that I want to make in my presentation is considering these kinematic and inertial loads and how they would combine during the time domain analysis. Because there is some guidance from the literature in which one can assume that based on the fundamental frequency of the structure and of the soil deposit, one can estimate whether these two loads would act in phase or out of phase to each other. So if we are looking at a stiff structure embedded within a very soft soil profile, the phase angle would be 0, so they would be acting in the same direction. If they have similar fundamental frequencies, we would observe resonance with a phase angle of 90 degrees. So these two loads could in theory be considered separately from each other. And if we have a very soft structure and a stiff soil profile, they would act by 180 degrees out of phase to each other. In cases where we observe liquefaction of the soil deposit, the soil is expected to be very soft, so we would expect this case of both kinematic and inertial loads acting in phase. We would expect this, and this could be confirmed through the validation study of the slender pile single degree of freedom system when plotting actually here the inertial forces acting at the pile top normalized versus both the horizontal displacements of the soil surface and of the pile head displacements. And this positive trend, so this positive inclination in this correlation plot here, this indicates that both of these are acting in phase, whereas resonance would be shown as a circle and an out of phase response would be shown by a negative inclination. And this is my last slide. And the point that I'm trying to make is that if we look at the superposition of these kinematic loads and inertial loads for two cases, so comparing now the slender pile study with the offshore monopile, for a time instance during the analysis where both structures would be pushed in the same direction, so from left to right, I'm showing the normalized displacements in the two cases here. The slender pile shows a distribution of bending moments that is expected for a cylinder pile that is embedded deep into the deposit, where basically it experiences tension on the left pile wall and a negative bending moment, and that really, when combined with a inertial force acting in the same direction, leads to the most detrimental combination of loads. Whereas for this stocky offshore monopile, which exhibits a rotation at its pile tip, actually the distribution and the sign mainly of the bending moments can be different. So we do observe in this case, as the pile rotates, a positive bending moment, so tension on the right-hand side of the pile. And as we see in this case here, the most detrimental combination which is taking place in this moment is as these kinematic loads and the inertial loads actually act in opposite direction. So there's no easy general conclusion to be made on how to combine these two loads in a pseudostatic analysis if the displacement mechanism of the pile is such that it's able to rotate around its tip. This leads me to the conclusion. I hope I was able to show you that there are some valuable insights to be gained from these advanced numerical analyses. And to summarize, the main points that I made were the risk of resonance on a offshore wind turbine structure if a large extent of the soil deposit liquefies, as well as the effect of higher mean effective stress levels near the pile shaft compared to the free field, which are not normally considered in standard design, as well as the different effects of the combination of kinematic and inertial loads. And I'm also, just for the reference, showing you the sources. Thank you.
Thank you, Kika, for the fascinating presentation. And now the final speaker for today's talk is Vangelis Kementzetzidis, who has been a lecturer at Delft University of Technology since March 2022. He recently completed his PhD thesis on the soil structure interaction of large diameter monopiles in sand. So to date, he has published 4 journal papers on this topic, and additional publications are underway and under review. He was recently awarded ICE's David Heslop Award for the paper frequency effects in the dynamic lateral stiffness of monopiles in sand. And so I'll hand over to you, Vangelis, and yeah, please, I can see your presentation is already on. All good, thank you.
Thank you very much, Marco. Hi, everyone. Thanks for coming to today's event of SECED on offshore geotechnics. I would like to thank Marco and Stamattina for inviting me. I guess he was the previous chair of SECED. Yeah, so let's proceed with the presentation. My name is Evangelos Kementzetzidis, as has already been discussed. I'm from TU Delft. My presentation has the title Monopile Response to Lateral Cyclic Loading. So let's proceed with it. Short introduction has already been made, but I'm going to repeat a few highlights. So I come from Greece. I obtained my Master of Engineering in Greece, and then I moved to the Netherlands to TU Delft, where I did my Master's, my PhD, and where I'm currently a lecturer. Today's presentation will mainly focus on findings that came from my doctoral research, but also some work that has been done afterwards. The title of my dissertation is Cyclic Behavior of Lateral Loaded Monopiles in Sand with Emphasis on Pile Driving Effects. And I would like to acknowledge the guidance and help of my supervisors and my promoter, Andrei Metrikin, and my supervisor, Federico Pisano. I would also like to mention that the research that took place during my PhD was funded and was part of the Gentle Driving of Piles project, which we're going to discuss a bit what it is a bit later on. Let me go to the next slide. I would also like to acknowledge the help of all the people involved in the GDP project. These are the main people behind it, and I'm one of the PhD students that was driving the research on the lateral behavior of piles in sand. So I'm talking about GDP, Gentle Driving of Piles. Let me try to, well, the video is not, okay. So let me try to give you a bit of motivation before we go into what exactly it is. So as Stavroula mentioned during her presentation at the beginning, one of the main concerns during pile driving is the noise that is generated and that is emitted through the water. And the reason that this is a problem is that this is harmful for marine life. So for that reason, regulatory bodies set constraints to the noise levels during the installation of a wind farm, for instance, which lead to offshore engineers to adopt costly underwater mitigation measures, for instance, bubble curtains. So this is where GDP comes in. GDP is a new monopile installation method, which is essentially foreseen to reduce monopile installation noise when monopiles are installed. And to explain why, we need to understand a bit where the source of the noise comes from. And the source of the noise is mainly attributed to the piling method, where it's mostly attributed actually to the driving loads. So we have a monopile. I hope that you can see my water bottle, for instance. And the currently most selected driving method is impact hammering, impact piling, where essentially what you do is you place your monopile into the seabed and then you apply a series of hammer blows into the pile head to achieve gradual penetration. So where the noise comes from? Well, each blow generates a compressive wave that travels through the monopile, and due to the Poisson effect, locally as the compressive wave travels, the monopile expands laterally, and that radially, and that radial expansion is essentially the source of noise. So the point is, if we're able to reduce these vertical driving loads, we're going to be able to reduce the noise. The first step towards that direction is the conventional axial vibratory driving. In that case, there's a harmonic load, vertical harmonic load applied on the monopile head, and then this is the way. It's a gentler type of installation method, but this is essentially what drives now the pile into the soil. An axial, a vertical driving harmonic load. Now, the GDP method is another vibratory method, but enhanced. So essentially, we keep the axial component of the axial vibration, but we enhance it with the torsional vibration. So the pile rotates like this as it's driven into the soil. And why do we add that component? Why that component was foreseen to help, at least, is because, well, first of all, torsion will not cause the pile to radially expand or deform. Plus, this high frequency torsional motion is foreseen to consume, and it's also shown to consume the shaft friction, and hence you're able to drive the pile with just a lower amplitude vertical load. So that's the concept behind the GDP driving method, which where around it the GDP project was built, and it started with the creation of a shaker, so a shaker that is able to apply these motions to allow us to drive the pile with the GDP way. So there was an idea, now there was a project and a hammer. So we needed to essentially demonstrate that this method works. For this reason, GDP field tests were organized. They took place in the port of Rotterdam, in a sandy site in Maasvlakte. This is an aerial picture of the site. This is exactly where the test took place. And just some highlights. 3 different driving methods were used to drive 8 piles into the sandy soil. After all piles were installed, they were clamped. Well, lateral loads were applied to the pile head for 82,000 loading cycles, and then so all this done were for us to be able to assess the installation method, the impact of the installation method, the performance, the driving performance for each pile, but also their post-installation behavior, and to encourage that. The ground in the site was excessively monitored, but also the piles that were driven. And all of the findings some of the findings actually I'm going to discuss now, I'm not going to discuss everything. They will be hopefully soon published in 2 publications, Tzetas et al. And Kementzetzidis et al. But these are in the final review stage, so they will hopefully be out soon. Well, this slide has already been discussed by the previous presenters, but just let me give an extra bit of motivation. Why do we care about the lateral loading bit, which was the core of my thesis? And it has to do mainly with two uncertainties. So offshore engineers need to be able to create structures, offshore wind turbines, that their natural frequency, the first resonance frequency solid, will be in this small region where there is no external loads. So the frequency of the external loads is minimum at this region, and offshore engineers would like to be able to develop offshore wind turbines with the resonance frequency that just lies within that short range. And additionally, you have an offshore wind turbine is loaded through winds and waves for many years. You can understand that the structure will tilt a bit, and for this reason, certification guidelines set very strict limits on how this tilt on the monopile can develop, how much can it go. And although there are strict limitations, the tools that we have currently cannot really provide us all the answers. So that's why this research topic it's quite fruitful. So going back from motivation to the project, let me talk to you a bit about the Maasvlakte 2 site and how, like an overview of the experimental campaign. So 8 piles were installed. These are the ones that you see here. And in the middle, there was a reaction pile to allow us to apply lateral load into the piles. The rest of the presentation will focus on 4 piles, each of them installed with a different driving method. So the red pile, the colors will follow during the presentation. So the red pile is the impact hammer pile. The blue and the black piles, the colors represent GDP1 and GDP2 piles, and the green one is the vibrohammered pile. All of these 4 tested piles had an embedment length of 8 meters and a diameter of approximately 0.8 meters. If I can get your attention here to the right, so site investigation was performed, an extensive site investigation was performed. I'm just going to show a few details here. So we have CPT test, SCPT test actually. This is a cone penetration, so a cone resistance over depth for the 4 piles. From the cone penetration, we're able, cone resistance, we're able to infer the relative density, and also there is an independent measurement of the shear wave velocity because these were seismic CPTs. And what we can see, what we unfortunately saw was that the sandy mass flux side was quite inhomogeneous, and that you can see readily by looking at, well, relative density or the cone resistance. You can see, for instance, that the pile installed with the vibratory hammer method, the axial vibratory hammer, was in the loosest part of the site. The GDP2 pile was in the densest part of the site, and impact hammer and GDP1 were somewhere in between. Now, moving on to the lateral loading tests, which are the focus of this presentation. In each of these 4 piles, so you can see here a picture, a side picture with a reaction pile connected to a test pile, and this is the loading frame. So each of these 4 piles was laterally loaded for 42 hours, approximately 82,000 loading cycles. Here you can see the amplitude of the lateral loads applied. And with black, the black color depicts parcels of slow forcing by high, slow forcing 0.1 hertz, but high forcing amplitude. And these were in total 5,000 cycles of strong amplitude loading. And in between them, you see these gray parcels. These are small amplitude parcels. So the range was 5 kilonewtons with different forcing averages. You can see that the average of the forcing changes depending on the parcel. And these were frequency sweeps, meaning that the starting frequency was 0.1 hertz, which was gradually increased up to 4 hertz. And they were placed during the loading program at various places, locations, to allow us to get some information for the dynamic response of the piles, the dynamic behavior of the piles, but also indications of the evolution of small strain behavior of the pile. So these are small amplitude tests again. In a nutshell, these are the tests which we're gonna discuss further later on. These are the test results. Sorry. So here we have a load over displacement, and we see the 4 piles here. In black is the GDP2 pile and blue GDP1. Then we have vibro and impact hammer, again related to the site investigation to the left. What do we see? Well, first of all, we see that the GDP1 pile, the GDP2 pile accumulate the least amount of lateral deformation. And again, the accumulation of lateral deformation relates to the accumulation of the offshore with turbine tilt. This is why this is important, which corresponds very well actually with the soil profile, but then the pattern somehow breaks. And the idea is that, okay, we see 4 different accumulation patterns. Since the site was so inhomogeneous, how are we able to tell if that's an impact of the inhomogeneous soil profile, right? There are initial conditions, or it's an outcome of the piling method. Because you can understand when you drive your piles with different piling methods, the surrounding soil will be affected in a different way, will evolve in a different way, which will have an impact probably on the behavior after installation. So that's something that we cannot know just by looking at this picture. And a comment that I made before, there is noticeable differences in the accumulation, in displacement accumulation between the 4 piles. Something that must be, well, an additional challenge that was related to the site, to the mass flux site, had to do with the unsaturated topsoil. So the water table was located 4 meters below the ground surface, which was approximately half of the embedment pile length. And unsaturated soils, when you have piles installed in unsaturated soils or in cohesive soils, upon cyclic loading, you're probably going to see some pile soil separation, which was readily observed in the site. So here you can see some evidence to the right. So this is force displacement behavior during so the first cycle of high amplitude force displacement response of this is the impact hammer pile. You can see the shape of the loop, and then you can see the last one, and you can see a certain evolution trend. Well, if we zoom in here, we see a kind of locking type of behavior, which is essentially means that when we increase the forcing to the pile, we see an increase in tangent stiffness. And this is a behavior that we should not expect to see in marine environments or in dry sands, for instance. And that additionally complicates the story a bit, but we're going to see how we deal with that later on. Further evidence of pile sol gapping. Well, we have pictures from the site, and as you can see here, a hole was left in place when we extracted the piles after the tests were realized, and you can see, for instance, that the sand here just is able to sustain a vertical slope, which is not something that you would expect in a in dry or water saturated sand. And also, to the right, after the lateral loading tests were completed and the pile was at rest, you could see a gap between the pile and the soil. So let's start looking at the results. Now we're going to show these results are not modeled. These are just post-process results as obtained by the field measurements. And what we're showing here is the evolution of the average cyclic stiffness of the four tested piles during the loading program, but now zooming into the large amplitude slow forcing parcels, so A, B, C, D, and A. What is the average cyclic stiffness? Well, let's see here on the right. This is a random force displacement loop that was obtained during the loading program for one of the piles. And essentially, the average cyclic stiffness that we saw is the slope of this line over here, connecting essentially peak displacement, peak forcing with minimal displacement, minimal forcing. And this is the trends that we get. And what do we see here? We see four piles, which are during the first parcel, so very, very different cyclic, average cyclic stiffness, very different. That's during parcel A. Then a loading program, well, the loading program progresses. And again, when we reapply the same forcing, but now named parcel B, but this forcing is identical, we see this the fact that the stiffness seems to homogenizes. So something that was very different at the beginning, something happened in between, and in the end, the result seems almost the same. And remember, the four piles here are with different driving methods and in a quite inhomogeneous soil site. Okay, and let's see what happens at parcel B. Again, during the first cycles, the stiffness that we saw was quite different, but then as the loading program converged, the cycles, the average cycle stiffness seemed to homogenize. And we have further evidence from that from the frequency sweeps. Here, for instance, we're showing the well, this particular frequency sweep. Here we have the average cyclic stiffness. Here I'm displaying the absolute value of the dynamic stiffness, but it's a similar concept for this in this case. And we see a quite different response, quite different cyclic average stiffness between the four piles at the beginning, but in the end, where at the end of the loading program, we reapply the same frequency sweep, you can see how the stiffness of the four piles has homogenized. And the same trend happens during the whole loading program. Essentially, something that was applied at the beginning, when we apply the same load somewhere near the end, we saw that all of the response of the four piles tend to look much more similar. And the evidence of this homogenization process, and the process, of course, is the cyclic loading, were also measured to a certain extent independently. So for some of the piles, before the application of the lateral loading and after, we performed impact hammer pile tests. That's not the installation method. So essentially, this is one of our piles. I hope that you can see that. We took a hammer and we just hit a blow on the side, as you can see on the picture here. And accelerometers were placed on the perpendicular direction to the forcing to measure the acceleration during this hammer blow. The hammer was instrumented with a load cell, so we know the input, but also the accelerometers recorded the behavior of the pile. And based on that, we're able to construct frequency response function for the 4 piles, of course, as a function of frequency. Again, tests done before and after the cyclic loads were applied. And what do we see? Well, for instance, if you remember the site investigation, we have the vibrohammered pile in the loosest part of the site and the GDP2 pile in the densest part of the site. So we have different installation methods and the maximum deviation, let's say, in terms of the pre-installation soil conditions. And indeed, that's depicted on the frequency response functions of the piles before cyclic loading was applied. You can see that they're quite different, and do note that this is in log scale. So the differences are all much more significant. Well, what happens after the cyclic loading? Well, then you can see it here again with green and black. So something that was quite different at the beginning seems much more similar after the cyclic loading was applied. So essentially, the point here is that the cyclic stiffness, and again, the cyclic stiffness is important when we're trying to design for the resonance frequency of the offshore wind turbines, seems that most of the differences, at least, that we saw on the site, soil conditions, but also driving methods, all of these differences somehow homogenized through the cyclic loading process to give us something that's quite similar in the end. So yes, I talked about the homogenization of the cyclic stiffness as it was observed on the site, but what about the accumulation of lateral displacements? Because we see that it's quite different between the 4 piles. And it's not only about the accumulation rate, it's also about the actual accumulation of the cyclic displacements, sorry. So the problem still stands. We need something that will allow us to account for the inhomogeneity of the soil if we want to shed light into if the differences in the accumulated displacement come from the installation effects or are an outcome just of the soil profile. So we need something that accounts for the soil inhomogeneity, and ideally something that is CPT based. And this is because CPTs are the only continuous measurement of the soil of the site inhomogeneity that we have. So we need something that will account for that. We need to account for cyclic displacement accumulation, of course, due to the fact that this behavior was exhibited readily during the experiment. So there was a certain kind of accumulation of displacement, which seemed over time to saturate, to decrease the accumulation rate. And also we need to somehow account for the gapping between the pile and the soil. And to do that, we formulated a cyclic soil reaction model, CPT based. So because there was a discussion by Kika before about bounding surface plasticity models, this model is also formulated as a bounding surface plasticity model, but of course this is now 1D. And there is a memory surface that controls, that modulates essentially the accumulation of lateral deformations. And you see that by changing a parameter here, we're able to obtain different accumulation trends. And this is the behavior in one way, and this is the behavior in 2 ways of the model. But this is for saturated or dry soil reactions. What about the pile soil gapping effect? Well, for that reason, we took that previous model and we incorporated it into a more complex set of springs, which are able to simulate the pile soil gapping. So what we see here is what we would typically expect of cyclic soil reaction in cyclic soil reactions to look like in unsaturated soils, so when pile soil gapping is enabled. And this model has already been published in Computers and Geotechnics in 2022. So if somebody wants to take a look, hopefully they will. And what's the strategy? So we took the cyclic soil reaction model that we developed and we distributed it along the pile. So the top 4 meters, when we have the unsaturated soil, we have the PY model that allows for pile soil separation. And below the water table, we don't. We just use springs that are able to represent drained or even saturated cyclic soil reactions. And let's look what we're able to do. So this is the experimental data. This is the force displacement behavior of one of the piles during the 5 parcels applied. These are the 5 large amplitude cyclic loading parcels. This parcel A, B, C, D, and E. You can see that during the last 3 parcels, the accumulation rate of lateral deflections has dropped significantly. And this is the outcome of the simulation of the model. And you can see that the trends were able to simulate it quite satisfactorily. pile soil gapping was reproduced, but also the fact that during the last 3 parcels, the accumulation of lateral displacement has to some extent ceased. Additionally, I showed you before the average cyclic stiffness, so the evolution of the average cyclic stiffness during the loading program. Well, we can simulate that because, of course, we have the loops. We can obtain the average cyclic stiffness. These are the 4 piles again with color on the back. This is the previous slot that I showed you, the plot. But with magenta now, we have the average cyclic stiffness as it came out of the model for the GDP2 pile. And what we can see is that the trends are simulated well, really well. So we have a model in the end that is able, CPT-based calibrated, that is able to reproduce the behavior that we saw on the field. Then what did we do? We took that model and we just allowed for a so the CPT-based calibration is still the same, like the formulation is still there, but we're able to tune some parameters, in order which would allow us to fit the behavior of the 4 piles in the GDP field. What we see here is displacement over the number of cycles for the 4 piles. So the solid lines represent the field tests, and the dots, the surrounding dots, give you the minimum and the maximum behavior as it was calculated through the model. So by fitting all the 4 piles quite well, and then by comparing the calibration settings, we were able to say that we saw right after installation, but now by accounting for the solid homogeneity, that the GDP-driven piles exhibited a stiffer response by 15 to 20% higher, which is good because if you want stiffer piles, then you can reduce the consumed steel. So that's quite satisfactory actually. But also, we saw that upon prolonged cycling, also by the model, the influence of the installation method on the lateral response, especially what lateral stiffness is concerned, appears to vanish, and that accumulation of the cyclic deformation seems to correlate strongly with soil profiles. Now we will go to the last part of my presentation. I'm going to talk about some research that is currently being done in TU Delft for monopiles, for the installation of the lateral behavior of monopiles. You can find all the details in grow-offshore window.nl, but essentially there is a GDP project 1.2, which is there to check the GDP pile driving method in clays. There's the SIMOX project for sustainable installation of extra large monopiles, and there is the MIDAS project, which I'm just going to show some highlights now. Modeling the long-term response of monopiles in sand. So in a nutshell, for the MIDAS project, we have centrifuge testing, which is quite important, well, for offshore engineering in general. We have monopiles in the centrifuge, and we load them laterally. Then the tests are modeled with 3D finite element analysis, and all of the insight gained through these processes is fed into the cyclic soil reaction model. So we want the cyclic soil reaction model that we discussed before, which probably is going to have additional components, additional spring components, not only the lateral PY components, and we want to enrich them with the knowledge that we obtain in order to provide to the industry a model that satisfactorily allows for the simulation of monopiles under lateral loading. And some fresh results. Unfortunately, I cannot show all the details because most of the data are confidential at this stage, but we have a monopile in 80% relative density sand of an L over D equal to 5, loaded with a high eccentricity. And here we see the force over the number of cycles. Of course, the values are not there, but you can see the trend. Each of these parcels is approximately 1,000 cycles each. And the idea is to simulate this test with a CPT-based calibration for elastoplastic cyclic soil reaction with thrusting control, the model that I just presented. And these are some test results.
I believe, Vangelis, you're muted.
Was it?
Thank you.
Okay. That has not been going on for a long time, I hope, right?
No, just one.
Okay.
Couple of seconds, yeah.
Okay, thank you, Marco. Okay, sorry for that. So what I was saying is that we observe here the global force displacement response between the between the piles in the centrifuges. So the global force displacement in the pile in the centrifuges. The displacement is measured here. I don't know if you heard that. And this is the trend that we obtained. This is during the cyclic partial of the highest amplitude. And this is what came out of the model. So you can readily see that the behavior is really, really well simulated by the model. Now, besides the first cycle and the first parcel, I mean, you can see that the loading program is quite complex, and we want to see if the features of this complex cyclic behavior, so this displacement now over a number of cycles for the full loading program, we want to see if the model is able to simulate these, and well. That's the results of the simulation. So you can see that the particular trends are quite well simulated. And then the last slide of my presentation is this one. So from the global behavior that we're displaying so far, we now zoom in a lot. So these are local soil reactions. And here, the local soil reactions from the centrifuge are inferred from bending moments from using Timoshenko beam theory in a procedure you can find well in the paper with the cyclic soil reaction model. And this is the soil reaction that directly comes from the model, because of course then we can look in really closely, and you can see that the behavior is quite similar, which is yeah, it's quite encouraging. That's all from me. Thank you very much for your attention. And yes, well, I guess there is time for questions now for all the speakers,
Sure.
but thank you very much.
Thank you, Vangelis. And yeah, before opening the Q&A, I would like to thank all the speakers for their stimulating presentations. It was great to see a wide range of exciting research works on this topic. And now we can finally move to the Q&A session. I can see there is a good number of questions already on the chat, so I'll try to go by in the same order that they've been posted in the chat. So the first question is for Kika, I believe. Is there any difference in mesh size based on relative density of soil?
You can hear me now? Yeah.
Yeah.
Well, the rules of thumb for establishing at least like the vertical size, the height of the elements, is based on the shear wave propagation, and this relates to the minimum VS of the soil, which, I mean, in case of the soil liquefying, then this VS becomes very, very low. But yeah, in general, it would be linked to the relative density as well of the material.
Okay, great. Yeah, of course, if someone wants also to interact, they can also open the mic and ask more questions. But I'll try maybe just first to have a go to the questions on the chat, and then we can open also the floor to live questions. There's also a question from Mahmoud Sadiq, like he's asking whether how you have selected the mesh size. I think that's probably already answered. And the second one is how you have selected satisfactory result during validation, 10% difference with your results. I don't know if you maybe.
On the first one, so maybe
Yeah.
I got the first one
Yeah.
wrong. If it was about like the extent of the mesh, obviously there is like a limitation of just the computational costs, and also that we do not want very long, like with a very high to length like of ratio of the element sizes. But in terms of the results, yeah, obviously, like as you could see, like the superstructure results were within such a narrow margin of like 10%, but some larger differences could be observed in, let's say, the free field pore pressure response, but that's expected for the calibration data that we have.
Right. And there's a next question is, I think, still for you. There's if you can expand on the pore pressure distribution in the ground and the FEM results for that distribution. And the second question is if you used any kind of contact element to model the soil structure interaction. That's from Abdiel Ramon.
Yeah, in terms of the pore pressure distribution, as I highlighted, there was this discrepancy between the far field and the near field of the pile, with like higher effective stresses near the pile shaft. And like vertically, since this was such a strong, more like shock type motion, one didn't see this surface downwards propagation of liquefaction that one might be used to from like more vibrational mode. So it all kind of liquefied very quickly, almost at the same time. But yeah, that was the reason for that. And the interface, so this was that there were interface elements used between like the soil and the pile shaft to enable a slip basically between the sand and the pile.
Okay.
Yeah. Is this the question?
Thank you. I think that's also answered one of the questions from Domenico Gaudio. I think that's also an additional second question is a question about the vulnerability to vertical components of seismic motion. So it's asking whether you believe that liquefaction can be beneficial thanks to the shifting of frequencies that you kind of discussed in the presentation. What's your maybe point?
So I have not investigated the compressional waves propagating, but in general, the non-linearity would be expected to be less significant than with like the shear wave propagation. So it would probably not be such a visible shift of the frequencies.
Yeah.
But again, I have not simulated them for this case.
Maybe Stavroula wants to maybe make a comment on this point.
Yes, I completely agree with what Kika said. While the vertical component can influence the deviatoric, particularly when it's close to the resonance of the vertical component. So when we have resonance in the vertical component, the deviatoric stresses can be influenced and can even aggravate liquefaction. So that's something we had shown before with the work of Vasya Chaparli. It doesn't work so much vice versa. So the nonlinearity in the vertical component remains usually relatively low. So while you might see a shift, I wouldn't expect it to be so significant, but it could be something to be checked in the future, I suppose. Yeah.
Thank you. I think there are a couple of specific questions still for you, Kika. One is about the pore pressure traces from the FE analysis using the model M2, where there's an abrupt onset of liquefaction with regard to compared to M1. So if you can comment on this.
Yeah, that would be expected from this very low inclination of the cyclic resistance curve. So what this low inclination meant is that basically the soil is much more vulnerable, like when there's a change in the stress level. So for like, a higher peak, suddenly the liquefaction resistance is much smaller. But then the slow inclination means that at lower amplitudes, it's much stronger. So if there's like an abrupt motion, so basically at the beginning of the motion during the lower level excitations, there was not a strong increase because of that, but then it liquefied fast for the high stress levels. So yeah, that would relate to the CSR curves that I showed on the slide.
I see. Okay, that's great. And second question from Danielle is if whether you believe like there's a need to include in the FE model the effect of hydrodynamic added mass on the wet portion of the monopile during the earthquake induced motion. Do you have any comment on this?
So one comment, maybe I didn't make it very clear in the presentation, but all the analyses are fully hydromechanically coupled. So the interaction of the fluid and the soil is already taken into account. But I'm not sure if this is what the question
is about. Well, maybe I think I will always invite also if there are specific questions to interact with.
Sorry, Marco.
Please, yeah.
Yeah, if you don't mind, I can.
Please, yeah. More than welcome.
Question myself. Now, maybe I wasn't clear in my question, but I referred to the free portion of the monopile. Let's say the part that sits between seabed and the water table. There, you in reality you may have an interaction between the monopile and the actual water, the water, right? While vibrating, the monopile may move a certain amount of water, and that would be translated in the dynamic response. It would feel as an added mass, right, to the system. Obviously, that the need to account for that, it depends on the amplitude of the motion. I was wondering whether a monopile under earthquake loading would move sufficiently to mobilize this added mass. In that case, it would be needed to capture it in the FE model. Typically, this is done by adding lumped masses to the tower beam, because you cannot do it otherwise. So just a curiosity whether you have looked into that or not.
I have not looked into that effect of the water on the pile, as you said. I mean, obviously there was also many other types of like loads and influence that I didn't acknowledge in these analysis. Like I was very in an isolated manner looking at the seismic response that was still also comparable to the centrifuge study. This is why there were no wave loads, no wind loads, because I wanted to be able to just compare these combined effects of the seismic loads together. But yeah, you're definitely right that in the future, like these effects of the water could be looking.
Can I add something to that, Marco? So yeah, that's something we haven't looked at yet. But in the past, when we looked at hydrodynamic effects in dams, the way we did it wasn't with an added mass, but with actually using solid elements in the FE model and assigning the properties of the water. In addition to using interface elements between the water and the structure or the soil, depending, and that worked very well. It's a publication we did quite a few years back of with Loisos Pelekanos in computer geotechnics, which showed that it's a very good way of modeling hydrodynamic effects without the simplification of added mass.
Interesting, very interesting. I may ask you the details of that publication.
Yeah, I'll put in the chat. I'll try to find and put in the chat.
Thank you very much.
Thank you, Daniel, for your questions. And also, I think maybe Sabrula, you can address one general question that is in the next message on the chat is about, let's say, the growth and forecast of wind farm projects globally. And Rajit is asking whether there is any strong reason why North America is not much interested in wind farms compared to other regions across the world.
I wouldn't say it's not interested. Probably we're a bit slow in taking it up. So I think it's picking up now, and I suspect, and it's only guess, that it's mostly political decisions and depends on how offshore wind balances with the other sources of energy they're using, like shale gas or you name it. And another aspect is to what extent the regulatory framework is mature enough. So sometimes some countries were slow in modifying accordingly their frameworks in order to be able to facilitate offshore developments. But I have to put the disclaimer that this is my guess rather than something that is based on specific knowledge.
Okay, thank you. And there's still one question for Kika is about the validation of the model with, let's say, any available field or experimental results like centrifuge modeling. Maybe I think you kind of tried to answer this point already in some of the question, but maybe just to clarify this in terms of validation. Yeah.
So if I understand correctly, in terms of the validation, there was just no centrifuge study that was publicly available for these geometries of the offshore monopile. So
yeah, I think
this is why
at one point I think that was clear from most of the presentation is the lack of experimental and case studies also. So in a way, I think this question from Rajit was more about understanding whether there was also other like available data that you could use, but I think you answered already that.
Yeah, I mean the shallow deposit with the slender pile that I showed seemed to me the most suitable for this purpose.
Sure. And I think there's a question from Omar about the coupling of horizontal and vertical excitations in terms of boundary conditions and the modeling of it. And is saying like boundary conditions, would you include at the bottom of the model to avoid P wave reflections and at the model line to properly model the water column?
So again, I have not simulated this, but in theory, I think that at the base of the model, the boundary conditions would be analogous to the shear wave case that I've looked at. Obviously, just like applying the vertical component as well. Whereas then to get like at the mudline level, I think we touched upon like in Savula's answer earlier a little bit. There are options to add interface elements between like the soil and the water, which have assigned this compressible, like the compressible stiffness of the water, but zero stiffness for like shearing resistance, to account for this effect when there's P wave propagation. But yeah, nothing that I have simulated. Yeah.
Okay, thank you. I think there's a final question for you, then I can move to Vangelis. It's from Susanna Lopez-Querol. She's asking whether do you think that the consideration of installation effects would have significant effects on the liquefaction successibility of the soil surrounding the piles? So yeah, she's also thanking you for the presentation.
Yeah, thank you for the question. So as I showed in the presentation, what maybe might seem a bit surprising, this increase of mean effective stress around the pile, when we look at these seismic and kinematic loads especially, they might not have a positive effect, at least not on the overall loads that we experience in the pile. So it is true that maybe that has to be considered more in future when looking at these installation effects. If they also densify and strengthen the soil around the pile, and if that pile then mobilizes the driving forces on the foundation during a seismic event, yeah, that I won't say it's worrying, but yeah, it might be more conservative to take that into account actually.
Okay. Great. And then now we can move to a few questions for the second, let's say, the final presentation of today's seminar. So there is Wayne asking for about the hysteresis loops observed in the centrifuge test and the field test that look a bit different. So he's asking about whether there's any effect of gapping. And about slide 10, so quite a specific question, what is the height of the loading points?
Okay, I was able to track the question to the chat. So for the second, okay, so the difference in the hysteresis loop in the field test and in the centrifuge, it's mainly attributed to the unsaturated topsoil. So in the field test, we have unsaturated topsoil, which allowed pile and soil to separate. This didn't happen in the centrifuge because the sand there was dry, and that's the reason that you see those peculiar kind of locking type of behavior on the site and not observed in the centrifuge. That was an additional challenge that I talked about. And for slide 10, what is the height of the loading point? Maybe it's not worth sharing, but okay, slide 10 is the one. So the slide 10 refers to the field tests. And that's a good question. I guess I didn't mention that. The loading point is 1 meter above the ground level, and the displacement are measured right in the soil surface. Okay. So this is in regards to the field test that I presented.
And then there is a question, a couple of questions from Kushik. He's asking whether you account for the effects of cyclic loading on saturated soils in the FEM analysis, and whether you have incorporated a BSP model in the FEM. And you may have already mentioned that in the presentation. If you could just clarify this point for our participant.
Yeah, thank you, Marco. So for the unsaturated, for the response in the unsaturated soil, the cyclic behavior of the unsaturated soil, well, the unsaturated part, let's say. So the idea is that the unsaturated soil, right, the saturation degree is lower than, it's not fully saturated. It allows for a pseudo cohesion to develop into a sandy soil, otherwise cohesionless soil. And this has the impact of allowing the pile and soil to separate. So indirectly, the effect of the unsaturated soil was implemented into the FE model by allowing for pile soil separation. So that's how this was dealt with. And have you incorporated the BSP model in FEM? So the cyclic soil reaction model that I presented, especially the one that discusses, well, the cyclic soil reactions in drained or in saturated soils with ratcheting effects that's framed in bounding surface plasticity, and this has been implemented at the moment in the OpenSea's finite element framework. But well, at some point, I guess this will become public. We'll load it into the repository of OpenSeas at some point. But yeah.
Great. And Omar has also asked a question for you about the sufficiency of standard CPTs for calibration of the advanced PY, or there are also other lab tests that may be required.
That's a very good question. So to some extent, this additional information will get through the MIDAS project. So when we did the site test, we just have 4 points to compare, right? We have 4 CPTs, and then we needed to infer all the parameters to calibrate based on the CPT-based calibration. Of course, the CPT method is based on a paper from Suri, Santana, and Lehen, where they did some studies with finite elements to obtain this the CPT-based calibration formulation. But well, the MIDAS project will allow us to obtain tests of lateral loading piles in the centrifuge. There are CPTs that are performed in the centrifuge, and we're going to analyze them with 3D finite element analysis, and then hopefully the information that we get out of these 2 tasks will allow us to shed more light to this. But that's the hope, that at least, for instance, in say normally consolidated sands, right? If you don't have a lot of like locked in lateral stresses, then hopefully it will be able to achieve this. Yeah, that's the plan.
Okay, and that's a very good answer, I believe, for Omar. And I'll just cover the final 2 questions because we have already, let's say, exceeded our slots. If the speakers have a few minutes more to stay online. And there's still one question for you from Susanna about the 1D model. Is there any way to consider the degradation of the soil due to the accumulation strains? And also to make an analysis for the long-term response, would you consider extreme events only, or the dynamic loads during the whole life of the infrastructure?
Okay, thank you very much for the question. I'm not able to find that exact, but okay, I remember what you said.
Yeah, towards the end of the chat. Yeah.
Okay, so well, about the degradation, well, if we're talking about dry sand behavior, for instance, or saturated, but not with a lot of pore pressure effects, typically we see that if we load it cyclically under nominal loads, it will actually improve. Like it will stiffen. That's what we see also in the test. Like it will stiffen. Of course, it will accumulate some deformation, but the stiffness will increase. So the degradation that we saw on the site, some kind of degradation, was due to the fact that pile and soil allowed to gap, right? So that was some kind of nominal degradation that we saw. But mainly, I guess, these will relate to clays, for instance, because when you cyclically load clays, they destructurate and they degrade. That's not at the moment in the model. Hopefully, it will be extended to do also cyclic PY behavior in cohesive soils like clays. About the question of long-term response and consideration of extreme events, well, the model is not supposed to only be able to do that, right? The reason that I showed only the large amplitude parcels from the site was due to the fact that these were the only ones that actually altered the foundation response. So the frequency shift that we put in between didn't do anything. Like we were able to observe that. So there is the idea that, yeah, we want to be able also to predict the nominal behavior, but large amplitude, like strong events, are the ones that evolve the foundation, let's say the behavior of the foundation. But well, if you want to do the whole life, like if you want to design for the whole life behavior of the monopile, you need to be able to account for the impact of these large amplitude events on the behavior of the monopiles during afterwards nominal loads, because then the stiffness and the accumulation will evolve. So that's important.
Thank you for your response to Susanna. And final question is from Helen to Julia. She's asking whether you have extended your research to look at the impact of seismicity in anchor design for floating offshore wind farms. Saying like many of the deep water floating sites will be located in high seismicity areas, Italy, west coast of the US, and offshore Japan. So she's definitely will be a point in understanding like the impacts in terms of seismicity for the reliability of anchor and the impact of potential tsunamis in these areas. I think that's something also Stavroula have touched upon in her introduction, but I don't know, either both of you maybe want to have touch on this.
I mean, yeah, I mean, obviously, I do agree that if we want to expand like these offshore wind farms into deeper waters, like way more research needs to be done on these floating types of foundations. I have not looked into them yet myself. Obviously, as you could see from my talk, like I focus a lot of my research on the liquefaction of the seabed, for example, and obviously there are issues related to that with how deep like the foundation would need to be embedded not to remain stable under these conditions. So yeah, lots to look into, but nothing I have yet researched.
Okay, great.
Yeah, I guess in floating will be whether there will be extraction of the anchors in case of liquefaction. So yeah, it's a very interesting. I haven't looked at it either. It's we start slowly going towards a direction, but yeah, the monopiles are still quite
yeah,
the focus. But it is Helen is absolutely right. We need to start looking at floating as up.
Okay, great. So that brings to the end of the talk, and I believe it's been a very inspiring talk and great presentations from all the speakers. We have also had a very successful attendance, more than 220 people joined today. So the recording will be available in the next few weeks through the YouTube channel. So if you miss part of it, you can still like watch it for free at any time at your convenience. So thank you again, Stavroula, Kika, and Vangelis for your time today and for the presentations, and see you soon. Thank you to all the participants. Bye.
Thank you, Marco. Thank you, everyone.
Thank you, Marco.
Bye.
Thank you all. Bye-bye.